Perfect. Final talk of IWOCL this year is from Peter Thurman from the University of Innsbruck, who's going to be talking to us about Striding data movement on GPUs. Thanks, Peter.
Thank you. So yeah, I talk about something that I thought would be really simple, and which I still think should be really simple, but which turned out to be a bit more complicated in the end, which is moving just a column basically of data from one GPU to another GPU. Great. Okay, so let's start with a bit of background. Basically, you can imagine, as we saw this week quite a few times, you have for simplicity a 2D space where you do the domain decomposition, and when you are doing domain decomposition, then you have to move some elements from one GPU to another GPU. Now, when you're moving those from a row to another row, as you can see in the blue here, then this works very efficiently in general because you have a contiguous block of data and you're just moving it. Now, when you need to move the column, then it can be more problematic because then you have a strided data layout. And of course, in higher dimensions, it gets even more complicated. And yeah, we saw this already on the first day of IWOCL this year in two ways, actually. So in the keynote, we heard that all the data is manually basically linearized before being transferred, because otherwise it would perform worse. And also, even on FPGAs, which has very little to do with what I'm presenting here, it was interesting to me that Christoph mentioned that they found that their north-south splits were a bit more effective than the other way around. So this is probably also related to this effect. So for us, the motivation to look into all of this is because we're working on the celerity system, which basically implements a rather SYCL-like interface for targeting entire clusters of GPUs. And so we very frequently have to move data around, obviously, and both across a few GPUs inside a single node, where we need fast transfers between devices, and also across nodes in a cluster where, depending on the cluster hardware and the API implementation and so on, we can use various methods, but on many systems, we often need to do a device-to-host transfer. So we also need for that to be rather fast. And now this is the one thing that basically motivated all of this work. So these performance results, which are pretty interesting and eye-opening, I would say. So what you see here is across both the main SYCL implementations and some representative hardware where you have consumer NVIDIA, consumer Intel, and Leonardo, which is data center NVIDIA. And what you see is different ways of copying a single column of floating point values between two devices. And so one thing I have in here, which you cannot see, is the result for just doing repeated 1D copies. Obviously, doing a 1D copy operation for 4 bytes of data is not a good idea. The reason I have in here is because with standard SYCL, and if you don't want to write a custom kernel to do this, then this is basically the method that is available. So obviously, I was there to get less than 1 megabyte per second. That's not surprising. What was really surprising to us when we tracked down the performance issue in another application is that when you do a native 2D copy, which basically maps, for example, to a CUDA 2D copying primitive, you get 64 megabytes per second, which is also not a lot of performance and can easily be a bottleneck, as you might imagine. So what you would like to get is more in this range for the consumer cards, which more or less gets close to saturating the PCI Express bus. So for reference here, the dotted things are contiguous copies of the same size. So that's ideally the best you can do for the striding copy. And as you can see, for most of these platforms, ours, which is the library I'm going to talk about, actually gets very close to the contiguous copy performance, but this is for strided copies between the devices. The only place where this doesn't happen is on Leonardo, because as you can see, the contiguous copy performance between the GPU devices there is on a completely different level, because they are directly interconnected using a V-link. But still, we get to 26 gigabytes per second there for the strided transfer compared to 5 with the native 2D copy. So that's the motivation for all that we did here. So what do we observe? I basically mentioned all of this by talking about the resides. 1D copies, repeated ones, are obviously not usable. Native 2D copies are better, and on data center hardware of NVIDIA at least, you can probably get usable performance out of it. On consumer hardware, they are still unusable. If you implement manual staging, so this was the part I didn't talk about too much here, which is basic staging. So what you can reasonably expect an application to maybe implement when it's not focusing on these types of copies. Then you can get rather decent performance, but it's about a factor of 4 off from what you can actually optimally achieve, which is still a lot of performance left on the table. And yeah, in all cases, it's possible to do far better than these options, but this introduces quite a lot of complexity to something which, again, I think should be easy. So our goal here was to build a flexible framework which basically allows the user to specify what they want copied, and then it does various things to that to actually make it fast. And yeah, so we looked at various strategies and then provide hopefully somewhat user-friendly library functionality to actually do the copy. Okay, so what are the basic elements for describing these copies and then implementing them? It starts from a copy spec, which describes one copy operation, basically. And this can be either the input to the whole system or an operation performed within a larger copy plan. So this is a source layout, the target layout, and some further potential properties. Then the next step up from that in complexity is what we call the copy plan, which is a sequence of such copy operations. So these have to be performed in sequence. And obviously the source layout of a predecessor has to be or the target layout of a predecessor has to be the source layout of a successor. And then these copy plans can be gathered in copy sets, which allow for the parallel execution of multiple copy plans at the same time. So semantically, in these copy sets, all the operations could be performed in parallel. Now, those are all the required ingredients for actually executing this stuff. There are some customization points for really covering the entire space of potential implementations that you could go for. And these are described in this so-called copy strategy, where there's a type, either direct or staged. This means staged here means basically linearized. So this means that manual linearization of the data is performed. And direct just doesn't do that. Then there are some other properties that describe how it should be implemented on the target platform. None means no special features. Use 2D means that it should use the underlying 2D copies when required and available. And kernel means that for linearization, if it's performed, it should use a kernel rather than copy. And finally, D2D implementation, or finally at least for the enums, D2D implementation describes how device-to-device transfers should be performed, either directly or with manual staging, in this case to host memory. And for host memory, you can distinguish further, should it be staged on NUMA systems on host memory, which is closer to the source or to the destination of the copy. This actually makes a difference on NUMA systems. Finally, there's the chunk size, which is for parallelization of the copy operation. Okay, so then how does this whole library work with all these components? As the input, you just have the copy spec. It just says that I want to copy this data layout to another data layout, either on the same device or on another device. And you have a strategy which describes how should this actually be done. Then first, if the strategy requires it, there's some chunking performed, which basically splits up your intended copy operation into chunks of some size, which are then put into a parallel copy set. So the simplest case would be the first half of the data, and the second half of the data, which you could imagine being the case here. Then there's staging, if again staging is required by the copy strategy, which could then change each of those parallel plans into a sequence of operations where first, for example, it linearizes, then it performs the transfer, and then it delinearizes again on different devices in the general case. And finally, there's also the device-to-device implementation phase, which can further split up operations which within the plan that go from one memory location to another to perform host staging manually. So here, for example, device to host and host to device rather than a direct transfer between devices. And then in the end, you have this more complex parallel copy set consisting of more complicated copy plans, and that needs to be enacted by the copy library. So now I'll quickly talk about a few things regarding the implementation. I don't have too much time to go into all the detail, but a few interesting highlights. In general, all of this is quite well tested. It was nice to split the theory, basically, of how this is performed completely from the implementation. That made it easier to test. It's very important to keep everything asynchronous if you actually want to get close to this peak performance. And what we found is that at least at this very low level and at the very small kernel runtimes that we're dealing with, submitting to manually managed in-order queues was a lot more efficient than using an out-of-order queue. And on newer systems, I already briefly mentioned this, it's also important where you first touch your host staging memory. And we support 3 backends currently in this library: SymSycl, which is just for development and where the CI actually runs. And we have specifically tuned implementations with, well, unsurprisingly, DPCPP and adaptive CPP. So for DPCPP, a few things. The out-of-the-box performance here was actually already pretty good. And there are some extensions that are very useful for the purposes of this task of transferring data between devices. One of them is the peer access extension. So we don't need to use a vendor-specific API for that. One of them is, well, of course, memcopy2d gives us access to these vendor-provided 2D copy operations, which are much better than doing 1D copies, but as you see, for this purpose, not as good as doing it manually. And there's also into a queue immediate command list, which resulted in 10%, roughly 10% performance gain in some of our micro benchmarks. So I don't actually know exactly what this does, but it did help. I'm sure there are some people here who do know. So overall, it was very useful to have these things available as vendor-independent extensions, because then you at least don't need to specialize your backend for each lower-level API. For adaptive CPP, we use the queue custom operation to access the native 2D copy API, which was interesting because then we can directly compare the performance of the native one versus the layout extension provided by the SYCL extension. And well, very important, ACPP allow instant submission. At the beginning, I was wondering why is ACPP twice as slow compared to DPCPP. That's not my general experience at all. And so it was because we didn't have allow instant submission. And coarse-grained events also helped in some cases. And interestingly, manual thread placement was really important for ACPP, but not at all for DPCPP. In total, the tuned performance of ACPP was, in the most extreme micro benchmarks, 3.7 times higher than the non-tuned implementation. So that's pretty significant. Finally, very shortly, for linearization using a kernel, what we are currently doing is multi-versioning. It ends up with 70 kernel versions or something like that. And I was just thinking during the presentation yesterday, we could probably, if everything works out, throw all of that away and adaptivity level 2 will just do it. I really have to test out whether this is the case, but yeah, should be very helpful for this. Okay, then we get to the evaluation of all of that. I'll not talk too much about the experiment center. I already mentioned we have NVIDIA on either consumer side or data center side and Intel consumer. We did a lot of runs for this because all the benchmarks are really fast and the results are actually very consistent. This is not a strided transfer, so that's not what the library is about. This is the baseline, which is the absolute maximum we could reach with the strided transfer because it's the transfer of an equivalently sized chunk that is completely contiguous. So this just tells us what can these various devices achieve. There are a few interesting things here, which, well, first of all, we don't currently apparently use the NV-link on the setup with adaptive CPP as it was performed here. So that's why you have this huge device-to-device bar with BP C++ on Leonardo. And the other thing is, for NVIDIA CUDA backends, there's emulated device-to-device transfers, which are actually performed by CUDA when there's no hardware available to do them. These are not fast, as you can see here. So even for, this is a purely linear transfer, you can get more than twice the performance for the purely linear transfer by doing manual staging and chunking well. Okay, but that's not the most interesting part. What we really care about is transferring strided data. To do so, as we see, we have to linearize. And to linearize, as these performance results show, we should be using a kernel. I mean, the only viable options are either using a 2D copy and using a kernel. Again, individual just means one D copies, which doesn't make sense. It's just for completeness. But we see that on Intel consumer, and the same thing happens on NVIDIA consumer, the only viable option that actually achieves decent performance is using a specialized kernel to do the linearization. And on Leonardo, so the data center system, you get what I would consider decent performance with 2D copies, 4.6 gigabytes per second, but you can get up to 36 gigabytes per second with kernels. Of course, there's a slight trade-off between kernels and 2D copy because obviously the kernels are kernels, they actually occupy hardware that could be doing compute at the same time. So here's the final linearization performance comparison for the consumer NVIDIA system. Here we also did the pure baseline CUDA implementation and tried to optimize it as far as we could go, just to see difference. One thing we do see is that the 2D copy, this is not at all a SYCL issue, this is just how the 2D copy performs. It performs exactly the same across, regardless of how you access it. And the other thing we see is that even with quite a bit of tuning, we couldn't get the linearization kernel to perform as well, the SYCL linearization kernel to perform as well as the tuned CUDA linearization kernel. I'm not 100% sure as to this difference. On the other hand, it's also not that important because we're already at 41 gigabytes per second of linearization. That's a lot of bytes, a lot of columns of your matrix being linearized. Okay, now we get to the actual thing, which is we are doing a 2D copy, so a strided copy from device to device on those three testing systems. What you see here on the x-axis are different chunk sizes, from no chunking at all to 60 megabyte chunking, which happens to be the size of that data that's being transferred. So this is also no chunking, but it gives some nice symmetry in the chart. So this would actually mean, for example, that there are simply 2 chunks, and the number of chunks becomes significantly larger the further left you go on the chart. And then we have various ways of actually implementing the copy, with the main difference here being whether we use a kernel for linearization, which is the blue. Everything in blue is using kernels for linearization, and that's always faster than the corresponding thing without using kernels. And the other difference is between the lines in the same color, the upper ones, whether we are using emulated, as I mentioned, computer performs this emulated copy, or manual host staging for the device-to-device transfers. So D to H to D is with manual host staging. And as you can see, manual host staging plus linearization on the device using kernels performs by far the best. And what you can also see is that you achieve the best performance for this particular case with 1 megabyte chunks, which was one of the larger surprises for me. I expected to have to use larger chunks. So you can actually get down very small chunks and get good performance out of this. Again, 2D copy is down here. Maybe 2D copy without linearization. Now, I have the same data for DPC++, and I just have to slide it so that you can see that you don't see anything. I mean, there's one thing you see, which is that after all the tuning, adaptive CPP kernel launch overhead or synchronization overhead seems to be somewhat lower than DPCPP overhead, because you see the point up there for 0.5 megabyte chunks, which has the highest, where synchronization overhead has the highest impact. Obviously, you see that this one is the one thing that basically moves between those 2 charts. But that's more or less it. On Intel, well, on Intel, at least in the way I eventually got this to work, adaptive CPP, also not that surprising, doesn't perform as well in terms of overheads compared to DPCPP. Other than that, the overall shape is similar, but we see that there seems to be higher per kernel launch overhead or something, or synchronization overhead in general, because the peak performance moves a bit to the right to larger chunk sizes. Finally, on Leonardo, actually the best performance was achieved with 0.5 megabytes chunks, which was again one of the more surprising things to me. There's one option here which is not possible on the other systems, which is using kernels to directly write from one GPU to the other and back. And then you can even do something like have several kernel launches which write to the other GPU each to try to overlap this. This actually does increase performance, but in any case, you are always much faster linearizing on one device than just transferring the linearized chunks in an efficient way. So that was it. To summarize, we saw that on consumer platforms in particular, doing a naive transfer from one device to another of strided data is terrible. You basically need a factor of 10 or more performance on the table. And even when you have dedicated interconnects between GPUs, we can achieve an up to 5x performance gain by really thinking about how we do this strided transfer between the devices. But doing that is not really trivial, at least compared to what you set out to do, which is moving a few bytes. And so what you need is some optimized parallel copy plans that do appropriate staging for the hardware and the interconnect. You need high performance kernel-based linearization and delinearization, and you need an asynchronous low overhead enactment engine, I call it here, so basically the thing that actually executes your parallel copy plans. And that also needs to be tuned for each backend, because as we saw, the most efficient chunk sizes are so small that you easily run into any overhead that you could encounter. And so we made this library, GPU2D copylib. The name is very exciting, I know, which does all of that for you. There are some limitations to both this work on the one hand and the library on the other hand currently. So first of all, we did not investigate the impact of kernel-based linearization on potentially concurrent computation overlap. Obviously, there will be some, and the trade-off in an application that does very efficient communication and computation overlap will be different compared to what you saw in these baseline results. Another interesting thing, especially for us in the celerity use case, is looking at patterns of transfer involving more than a pair of GPUs, because then you might end up with more complex shapes of copy plans like trees or something rather than just a simple linear sequence. On the other hand, also we currently only do 2D copies as the name implies, but sometimes we need 3D copies or even more complex writes. And a lot of the effort of the library can be shared in that case, but it still needs to be supported. And of course, currently the library works in the way that you specify the copy strategy and then it does everything. For an end user, it would be much nicer to have some way of determining a good or good enough copy strategy automatically. So yeah, that's it from me. You can check out the library at the link above. You can also check out Celerity for all your SYCL on cluster needs. And you can check out SymSYCL for all your quick iteration during development and CI needs. Hopefully, that's it.
Thank you. Very interesting talk. So, if I understand correctly, in theory, it should be possible to do this optimization for just copy 2D, right? Copy 2D can just have a special case if it's one. Okay. So I think you should open an issue to Intel LLVM and say this sucks and you can do 10 times better and they will fix it, hopefully.
There are some, I do agree that 2D copy should just be much better, but there are some constraints that I don't have or that I think another implementation would have. So for example, this library obviously has to allocate all of this memory that it's using for the chunking, for example. As I was surprised to see, the chunks can be very, very small, so it's actually not a lot of memory, but still probably people don't expect their 2D copy invocation to allocate memory. So I don't know if you could do that. Probably it would be possible. And the other constraint is that going for the really high performance stuff here requires quite a lot of CPU because you are doing all of this very high frequency submission of kernels. And that's also something that obviously you don't expect when you just call 2D copy. So I guess it would need something like fast 2D copy.
Yeah, exactly. Because I'm not sure in the spec we put any restriction on copy. I agree it's weird. People will not expect that, but I'm pretty sure it may be compliant to have a copy who does this kind of stuff. Yeah, thank you.
Yeah, I guess my question is partially similar to previous one. So, in your opinion, is this a problem of copy of like sparse data, especially column data, is something niche which is better to cover through libraries and community work because of better flexibility? Or you think that is something which is supposed to be supported at the language level, even if it comes with some limitation and like rigid structure, because naturally standards more strict?
That's a very good question. I think this comes down to this difference or to these various user communities for standards like SYCL. So you have obviously maybe overrepresented in this room, you have the HPC community. And I think if it's just about the HPC community, this is not a niche use case. It's very common. You need it all the time. And from that perspective, I would say it should be part of the standard. But SYCL is not just about that community. It's also about a lot of communities where just having more than one device is the exception, right? And then, I mean, all of this still applies when you're transferring a column to the host system, but I don't think in those codes that's such a huge issue. So I really think it depends on the user community, and probably a good way to go would be to have an extension or something that's specific for more complex data layout copies.
Okay, makes sense. Well, and as another person have said, if you would like to see it upstreamed, I guess you need to go and put an issue in GitHub. Thanks.
Okay, great. Thanks very much.